Hello and welcome to the AI Research Roundup. I'm your host Alex, and today we're diving into some fascinating work in AI. We'll be looking at a paper called MMAudio, Taming Multimodal Joint Training for High-Quality Video to Audio Synthesis. The core idea here is about generating really good audio that matches up perfectly with video content. The researchers propose a new framework called MMAudio. What's really interesting is that instead of just training on video and audio data, they also bring in large text audio datasets, which helps generate better quality and more semantically relevant sounds. They also focus specifically on getting the timing right, the audio-visual synchrony. Okay, so figure 1 here really helps visualize this. It shows the MMAudio framework. At the top, you see the training phase, where it's fed both the traditional audio-visual datasets, maybe with some text labels like birds, and also these large-scale audio-text datasets, like birds chirping with soft leaf rustling. Both types of data go into training the MMAudio model. Then, the bottom part shows inference, where you give it some conditions, like a video clip, and maybe some text, like heavy rain, punctuated by thunderclaps, and the model generates the audio output, focusing on that semantic and temporal alignment we talked about. Okay, so Figure 2 gives us a closer look inside that MMAudio model we just talked about. Building on the general idea, this shows the actual network architecture. We see the video, text, and audio inputs going in, but what's really detailed here is this special conditional synchronization module. It uses a sync-former visual encoder to extract visual features at a higher frame rate, specifically to help nail the timing. These sync features, along with the regular visual and text features, feed into a series of multimodal transformer blocks, followed by some audio-only blocks, to predict the final audio flow. Right, so we've seen the architecture. How does it actually perform? Well, Table 1 here lays out the results for video to audio generation on the VGG sound test set. It compares MMAudio against several other methods across different metrics, things like distribution matching, audio quality, semantic alignment, and, importantly, that temporal alignment or synchrony we discussed. You can see the MMAudio models, even the smaller S16 kHz version, achieve state-of-the-art performance here. They show really strong results, especially in temporal alignment with a much lower desync score, and also better distribution matching and semantic scores compared to prior public models. Plus, it's quite efficient. Okay, so building on that performance discussion, Table 2 focuses specifically on the synchronization aspect again, but using different model-free metrics on the greatest hits dataset. This helps confirm the timing improvements we saw with the desync score in the previous table. You can see MMAudio, especially the S16 kHz version, gets significantly better scores in accuracy, average precision, and F1 score compared to the other methods listed. This really backs up the claim that MMAudio is great at getting the audio events to happen exactly when they should, according to the video. Okay, so those metrics are great, but what does this improved synchronization actually look like? Well, Figure 3 gives us a nice visual comparison using spectrograms. We see a couple of examples, one with a coyote howling and another with drum hits. Each row is a spectrogram. The bottom one is the real ground truth audio, and the rows above show the audio generated by different models, including MMAudio, which is labeled hours. You can see that MMAudio's spectrogram pattern looks much more similar to the ground truth, especially in terms of timing, like when the drum hits occur, marked by those green dashed lines, or the start and end of the coyote howl. It really shows how much better aligned the audio is compared to some of the other methods shown. We saw in the spectrograms how well MMAudio lines things up, but how crucial is that joint training approach using both video and audio text data? Well, Table 4 here gives us the answer through an ablation study. It compares performance when training with different data combinations. Just audio-video text, or the full mix. The results are really clear. The top row, AVT plus AT, which is the full MMAudio method, consistently gets the best scores across the board. For instance, the desync score is lowest at 0.483, much better than using only AVT data. The This really shows that combining those large audio-text datasets is vital for achieving that top-notch quality and synchronization. So we just saw how critical the joint training with audio-text data is for video to audio generation. Well, what's really quite interesting is shown here in Table 3. Even though MMAudio is designed for video to audio, this table looks at how well it performs on just text to audio generation, tested on the AudioCaps dataset. And surprisingly, it does really well. The MMAudio models, especially the larger MNL versions, achieve state-of-the-art or very competitive scores on metrics like clap score for semantic alignment and inception score for audio quality, compared to models specifically designed for text to audio. This suggests that the joint training really helps it learn a strong general understanding of audio and semantics, which benefits both tasks. So yeah, even though it's designed for video to audio, MMAudio shows surprising strength in text to audio too. I think the big takeaway here is really the power of that joint multimodal training. Using video, audio, and text together truly elevates the quality and synchronization for video sound generation. This pushes us closer to AI that really understands and generates richer multimodal content for all sorts of applications. Well, that's our look at MMAudio for this week. Thanks for tuning in to the AI Research Roundup. I'm your host, Alex.